New York, are you ready?
Maybe the camera should be on this guy's, not on yours.
Yeah, looks like it. And you have debaters.
Just far enough apart so that the camera doesn't see both.
We cannot hear you yet.
Cool.
Can the people in New York speak?
We cannot hear you. Can you hear us?
Say something in New York.
Are they trying to ask us something?
Oh, we can hear you now. Okay. So let's go for the first debate. Oh.
I mean, I am muted, I think.
Can they hear us? Michel, it seems that they cannot hear us. They should. Tu fais un coup de claque? Oh, not again.
Yes, we can.
Oh, you can hear us, right? Raise a hand if you can hear us.
Yes, we can hear you. Can you hear us? No?
Okay, we can hear you now. So let's start, and let me introduce Torsten Ensslin for the first debate of this week. Torsten.
Okay. Bonjour, Paris. Good afternoon, New York. Is there truth in latent space? So we have to find out in these 90 minutes. I'm Torsten Ensslin from the Max Planck Institute for Astrophysics, and we have an intercontinental debate by Saul, Luisa Lucie-Smith, François Lanusse, and Aleksandra Ciprijanovic. I hope I pronounced this correctly. Okay. Let me start with a short introduction into the topic, and then I will explain the rules of the game. I did the obvious thing. I asked an AI, is there truth in latent space? And it produced the following images. So on the left, we see how lost one is with this question. And on the right, I think one sees a direct view into the latent space. And of course, I wanted to have also a verbal answer. So I asked a large language model, and the answer was the concept of truth in the latent space is dependent on the context. In machine learning, the latent space represents hidden features of the data learned by the model, and the concept of truth may not directly apply. However, in philosophical or metaphysical sense, latent space may refer to a hidden dimension of reality, and whether it holds inherent truth becomes a matter of debate and personal beliefs. Nice distinction, but then I thought, well, these are actually very similar statements, right? If the data is our access to reality, and we are looking at a hidden layer, a latent space in machine learning or in philosophy, and we have problems to understand what the meaning is, we are faced with the same problem. So I was arguing with this language model until I got it to get the following conclusion. Therefore, in both contexts, the presence of truth in latent space is contingent upon the accuracy and effectiveness of the latent space representation in capturing relevant information or aspects of the world or reality. And I think that's actually capturing already a lot. How does this work? Well, these large language models, they embed the language in a latent vector space in which they can do operations. And then the big trick was, while it's called attention is all you need, is to structure this latent space by a weighting function which marks relevance, and then do operations on that. If we should define what we mean with latent space, so let's look at neural networks for a second. And most people would agree, if you look at a variation autoencoder, the latent space is defined by the variables of the thinnest location of the network. Let's call them x and y, and the space of possible states of that layer defines then the latent space. That can be directly generalized to generative networks. To any neural network, well, a middle layer defines a latent space. but the definition of the middle layer is not clear, so it could also be an earlier or later layer. So actually, I would argue, but there might be other opinions here, the latent space is anything which is not a data space. But let's debate, and let's start the debate with New York. Lawrence, well, before we get to you, let me first explain the rules of the game. sorry, yeah. So maybe I go back. The rules of the game are, I asked all the panelists, including myself, to prepare an as provocative statement as they are comfortable to make and explain them with a few slides. Then we will discuss between the panelists on the two continents and the audience for a total of 15 minutes, and then we get the next momentum talk. And so we see where this leads us. Okay, so New York, Lawrence, get ready, and can we switch the presentation to the New York presentation, to the same slide? Yeah, perfect, thank you.
All right. Everyone can hear me? I guess I'm in control now. Great. So is there truth in latent space? And while wrestling with this question, I came upon this centuries-old remark: all truths are easy to understand once they are discovered. The point is to discover them. And I think these words really do highlight the role of latent variable models, which is to discover the truths that are hidden in our data. They're also very fitting for this audience, in particular because of who said them. That's Galileo. The words belong to him. And if you don't recognize the picture in the middle, you may recognize the one on the right of his trial and inquisition, which is a reminder that in debates about the truth, the stakes can be very high. And so I thought that before blurting out anything that I might later regret, I should think very carefully about what I'm going to defend here. And so I came up, not being too original, with the following proposition, which is that all latent space models are wrong, but some are useful. And this is, of course, just a slight variation on the well-known comment by the statistician George Box. But it is the idea that models never really capture the truth of real-world data, which is necessarily quite complex, but that they are useful idealizations. And it is through these idealizations that we get partial glimpses of what might be called the truth. And to say anything more of substance, I have to be a little more specific. So let me comment on maybe the simplest class of latent space models. And these are matrix factorizations, at least the way I view them. Matrix factorization, a low-rank factorization, is just an attempt to write or approximate a very large matrix, say X, as a product of two smaller matrices, say W and H. And these factorizations can be viewed as producing a latent space model of high-dimensional data, since the columns of H are points in a low-dimensional latent space that are mapped by the action of W into the space of the data and into the columns of X, each of which records a particular high-dimensional data point. And most importantly, we obtain different types of latent spaces by imposing different constraints on these factorizations. And in particular, these different constraints can encode different geometries that we might like to discover in our data. So here's just a catalog of useful models that fit into this formulation. There's principal component analysis, or PCA, which is obtained by imposing orthogonality constraints on the factorization and revealing the subspace of maximum variance on data that's been centered on the origin. There is k-means clustering, which is obtained by imposing unary constraints on the factorization, which reveals a partitioning of the data. There is non-negative matrix factorization, or NMF, which is obtained by imposing non-negativity constraints on the data, and which can reveal some sort of sparse parse-based decomposition of data that is constrained itself to be non-negative. And there are also nonlinear flavors of matrix factorization, which have connections to models of deep learning and autoencoding that can reveal when, say, a sparse similarity matrix whose elements indicate which pairs of data points are similar arise from an underlying manifold, so a nonlinear geometric structure. And for any data set, I would say it's incredibly useful to know something about the number and the nature of its essential degrees of freedom. Degrees of freedom would be the way the physicists speak of the sort of underlying variabilities. And that's exactly what these latent space models, if properly applied with enough data and many caveats, can tell you. Now, do they reveal the truth with a capital T? I would say that you can be at different degrees of distance from the truth, and these models put you on the right path, right? So finally, I will end with these words from Plato, who thought harder than most of us about the nature of truth and geometry. So thank you. Open there, I guess.
Okay. Does someone wants to challenge this claim? Maybe I should.
Sure.
So let me try to get the position that if the data is our connection to truth, and whatever gets projected into the latent space via a neural network is just a transformation of the data, and therefore as true as the data was. So in that case, I would say everything is true in the latent space, right? The problem, from my perspective, is not that the latent space is lying to us, but that we might not interpret the latent space correctly. So do your geometrical views give us a better view on how to interpret the latent space, or how do we get to the correct interpretation of what the latent space means?
Okay, well, I opened with a very carefully worded statement, which is that all models are wrong, but some are useful. I did not say all are useful, or even many. And the caveat implicit in that wording is, yes, you have to be very careful about the models you apply and what comes out of them. So it is absolutely true that you can apply a latent space model if it's exceptionally uninterpretable, as some deep neural networks are. The information you've thrown away from the data and the information you kept may not reveal much. But I would say, I will stick to the original statement. If you're interested in the number and the nature of the essential degrees of freedom in your data, it's hard to imagine doing that without some sort of latent space model.
Okay. Lucia.
Can I be very provocative or
please,
become
absolutely.
a philosopher and ask to go back to what do we mean by truth? Because in different disciplines, it may mean different things. So many of us are here because we want to look up at the sky and learn something about fundamental physics. So our truth may actually be that fundamental physics, and we have another preconception that there is a fundamental physics there that we can understand, that can explain everything we see in the sky. So in this sense, the data are not the truth. So then you're gonna say, is fundamental physics hidden in the latent space? Is that the question?
You're addressing this to Nabila's answer.
Yeah, I mean, I fully agree with you. And in fact, I was a bit struck by what Lawrence has said. Many models are wrong, some are useful. It's not because they are useful that they're true. So what is truth indeed? And yeah, how far can we get into the very fundamental physics from the data? So I fully agree with you.
So still following Galileo, if nature is written in the mathematical language, then, you know, you are describing nature just by using mathematics as long as you're doing it right. So there's that too.
So if it's okay to spoil a little bit the statement I was going to make, but I think you're completely right, and it's a discrepancy between understanding the data and the model that can explain the data, which is what interests which is the question of interest to physicists, and just the question of being able to decompose the data or analyze it, where you can include a lot of your prior knowledge about what you expect from the data. So in some senses, discovering the model, which is the thing interesting to scientists, to physicists, I should say, or using your prior knowledge about the model to analyze the data or decompose the data in some interesting ways. And so I think the discrepancy in this truth is that some people mean the truth being understanding the underlying physical model, and for some other people is based on our understanding of those underlying models, discovering interesting ways of looking at the data. So I think that those are the two questions that are competing on this definition of truth.
And maybe just to add, oh, sorry, was there someone?
Go ahead.
Just to add, I mean, truth doesn't have to mean the same thing in every context, right? So you could say, well, my aim, my science goal for this thing is something much more low-key than fundamental physics, and is there truth in the sense of, is there some structure that I'm looking for in the data? Or you could ask fundamental physics questions and then say, okay, does my data actually contain that truth? So I think it's not a absolute definition of truth, but depending on your science question.
So I very much appreciate the George Box quote, because it points out, another way to state it is that, when I say all models are wrong, some models are useful, just a transformation of that sentence is truth is unattainable, but utility, but models vary in utility. And so perhaps the focus should be less on the word truth and more on the word useful. And so what do we consider useful? Do we consider useful something that we can turn into a mathematical formulation of a fundamental physics model, or, and clearly, there is a large field to debate, and I'll leave that to the debaters.
Well, I'll venture, and this will reveal my background in statistical physics as opposed to astrophysics, but I think it's the same idea. What can be very useful is when somehow you can explain a system which seems to have a huge number of degrees of freedom in terms of a much smaller number of essential degrees of freedom. In statistical physics, they would be the order parameters, but in other areas of physics, it's really the same, right? You want to find a compact description, and ideally, those are the things that a latent space would bring out. If we had the most useful model, I'll dodge the word truth, right? But that's my definition of, one definition of utility.
Nabila? Oh, who?
Oh, there's Benjamin first, I think.
Right. Taking this a step further, so as physicists, our job is model abstraction. And we agree that if we've got deep models, then the way to extract that information is through the latent space and the question of utility. So if we find we have deep models where the latent space is not clear to us, we can't make sense of it, what conclusions should we draw from that? Are those the kinds of models that are not useful, that we should therefore discard as physicists, even if they're performant at the end? Should we throw them out anyway?
The answer is no.
Answer is yes.
Okay. So you can have, as we said, we can have useful models. And so in particular, things like VAE, they are generative models. They allow you to represent complex distributions that can intervene in some part of your representation of the actual data. So in that sense, modeling distribution, it's a useful task. And so you can use that as a tool for that task, even though the latent representation doesn't make sense to you. But it's one way to parameterize the data, and you can use that inside a broader model, and it's useful. But then you may not be able to extract physical insight from the representation that's learned. That's okay. I mean, it is what it is. But now...
Well, I would argue then that is not useful, right? I mean, sure, you can have a black model that you have no idea what it's doing, is giving you perfect predictions about the universe, but at the end of the day, if we don't understand why it's doing it, what are the fundamental physics again, what are the generative factors that reproduce that data, I mean, then I would say it's not useful. So yes, you can get a great prediction. So there can be a black box model within a pipeline that allows you to then answer those fundamental questions, like that's fine. But I think ultimately that's not, you know, that can't be the goal. So I think maybe is there truth in latent space can be rephrased as how do we access that truth in latent space or in those abstract representations of the data?
Or which part of the model you care about. So we care a lot about physical parameters that, you know, make sense in our physical understanding about the system that we're studying. But there are lots of nuisance things that we don't really care about. Like I don't really care about the morphologies of galaxies. And so I'm perfectly fine having a model that can model that and marginalize that out at the end of the day. I don't really need to understand it. But for some other people, that's their science, right? And so that's where they will care about it. So you're perfectly right that I think we should think about this compositionality of different parts of the model. And there are parts for some science you care about and some that you don't need to be interpretable.
Before we go to Nabila, there was a remark on this thread in New York, and then we go to Nabila.
I think Douglas.
Yeah, partly I was just trying to interrupt so we could get a question in New York. But Brice Menard brought up the issue that some of the data that we look at is not nearly as complex as what a lot of people doing machine learning are looking at. And then we were told by our presenter here that there are, you know, that no models are correct. But I think in cosmology, I think most cosmologists think that the underlying model is correct and that the thing is much simpler than telling cats from dogs or something. So there's a power spectrum which describes the data except for the completely Gaussian randomness. So in that context, are the 6 cosmological parameters that describe the power spectrum the latent space? Because if they are, I mean, if that's just an analogy for how you would do it with machine learning, if they are, then there's truth in latent space because we believe that the 6 parameters describe, as far as we can tell, all the data that we have. So I think in cosmology, the answers to some of these questions are different because it's simpler. It's not a question, really. Sorry.
I guess I would partially agree because if we agree that the parameters that we know about fully describe the data, but what if there are additional parameters? Maybe there is some non-Gaussian behavior that might be better explained by adding something additional. Would AI be able to somehow figure this out better than us and somehow embed it in a larger latent space that has more parameters, maybe a few more, maybe one more, but that would actually better describe cosmology, even cosmology. So I necessarily don't believe that like the latent space always has to align with what we would do naturally, I guess. So that doesn't mean, my personal opinion, and if we don't understand how to interpret the latent space, that doesn't mean that there isn't truth in it. But I would also add that, in my opinion, truth is only related to the data. And I think as scientists, we usually are only it's only acceptable to comment about the results of an experiment or a measurement based on the data set. And we as a community, in the end, agree if we believe that this is the universal truth about this particular phenomenon. And there are many cases in history where new data actually changed our minds. So I think, in my opinion, debating about the truth can only go as far as what is the truth related to the data set that I have at the moment, not the universal truth about the phenomenon. I don't know, that's partially a comment to your comment. Yeah.
Let's have Nabila before we get to the next momentum talk.
Yes, so I understood that, Doug, you wanted to bug me even with the ocean parting us. So now I wanted to just ask a question that is, from what I understand, the truth, or at least the, let's say, utility, is essentially having a compressed information which can be interpretable. But the problem with the data is that I mean, for us here, or the way we talk about them, I mean, the data are God-given, which is not at all what they are. The data are processed. I mean, the data come from instruments, from telescopes, from pipelines, and this is why, I mean, I have some kind of difficulty in describing the data as really the truth. I mean, they are also a rendering of maybe some sky via observations, and this is either taken into account in the latent space, and in that case, the information has also to fold in those effects, or we're just failing because we have to make the difference between what the data tells us in terms of the physics, let's say, and what it tells us in terms of the data themselves, the way that they are produced.
Okay, thanks. Let's come back to Paris. For the presentation of Luisa. You're online.
Okay, so let me. Okay, so I just want to make my statement in a brief, like one slide thing, with saying that what can we do? Okay, is there truth in latent space? Yes, there is, in the sense that it is designed, these are networks that are designed to describe structure in the data. And so our assumption is within the data structure there is truth. So then the question is, how do we actually access that truth in order to learn something about some sort of scientific discovery, learn something about science? So what we typically do with these latent spaces is that we have some raw data. I mean, in this case, I'm just going to present like an example to give the general broad idea of how I would do this. Which could be, say, your cosmological simulation. So this would be like your data that you're trying to compress into a low-dimensional latent representation. And then the way to make this interpretable is to essentially impose constraints to that latent space so that you encourage that latent space to resemble the physical factors that have generated your data or whatever. So one way to have this constraint is to, for example, ask the latent space not to contain all the information in your data, but just that relevant to predict a certain output. So this is just an example where you don't actually, like a standard VAE, you don't reproduce the entire input data, but just one aspect of it, one observable, for example. And so here, your latent space is actually constrained to only contain information that is relevant to predict a certain output. So how do we access this truth in this latent space? I think is basically via two things. One is making this latent space interpretable, and that can mean various things. I think one way to do this is to basically have a compressed latent space that is low dimensional. So this is really important. You know, we can't interpret latent spaces that have thousands of dimensions. So low dimensional, compressed, and for example, disentangled. So this means having different latent parameters capturing independent degrees of freedom in your output. And then on top of being interpretable, it also has to be explainable. So you actually have to be able to map the information in those latent variables to something related to your science domain. And this you can do, for example, via various information theory metrics, such as mutual information, via different, for example, linear models to relate the information captured in the latent space to some physical parameters of physical outputs. So that's how I think we can access truth in latent space, and that's it.
Thank you. Good. Anyone questions this? Yeah.
There is one question on Slack from Victoria Villar, which is anyone actually trying to extract new physical insights from latent space? Isn't the much more common task attempting to regularize the latent space with non-physical truths?
Sorry, can you repeat that?
To summarize a bit, is anyone actually trying to extract new physical insights from the latent space instead of just looking at the physics that we know is true?
Yeah, I don't think, for example, when you're doing something like this, you don't need to know what the true physical parameters are in the first place, right? You can just try to encourage to resemble something like what we typically have in physical models. So that would be trying to have a latent space. This is, for example, the disentanglement comes in. So trying to have a basis for your model that separates the independent degrees of freedom. But you don't have to know what those independent degrees of freedom are in the first place. Yeah.
Is there actually something on Slack going on?
It was from Slack. That was from Slack.
Hi, thanks very much for that kind of presentation. So I guess you still have a black box that you don't really understand, and you're trying to somehow explain the outputs of that black box. But, you still don't actually understand the black box. So what about, on the other hand, instead of trying to, in a sense, guide that black box so things are explainable, to actually have a white box in some sense, which is interpretable and you can actually understand what that is doing, not just its outputs?
I guess it depends what you want to understand, right? I mean, if you want to understand what information is capturing from the data to, for example, predict something or even reconstruct your data, then the latent space is a good place to look for that. If you're trying to understand, for example, what hierarchical or abstract representation a convolution neural network is learning, then you would have to make it somehow a white box, but that's a much harder task. So I think interpretable, I guess it depends on what you want to understand from the network. Yeah.
If one looks at a network which we find produce very interpretable output, our own brain, looks at the internal representation of the different layers, it's completely black box. It's very hard to understand. It changes from layer to layer, even seems sometimes to change from time to time. So maybe we have to accept that there is no easy way to understand these representations. But there's a question here, and New York is somehow making a signal if there's a question, or because I don't.
Yeah, there's a question from Laurence after that.
So yeah, Laurence, please.
Me?
Yeah.
Okay. So I guess maybe this is a question, but I often think we think of these models as helping us to make positive discoveries. We add some constraints to the latent space. We have a very powerful black box neural network. Can we discover that the latent space, there are a certain number of degrees of freedom? But I wonder, and this is more of a question, do we trust these models to help us make negative discoveries? I mean, they're so powerful. Do we believe that if we can't auto-encode the data down to a certain number of neural network hidden units, that in fact such a low dimensional description is not possible? What does that count? Is that even in the realm of something you would want these models to discover?
So just to bounce back on that question, there is like something that has been puzzling me for a long time, is that a neural network can encode information down to a very small number of units and then decode it back up. And so it's not clear to me that just, like the bottleneck of your autoencoder is actually telling you anything about the intrinsic degrees of freedom of your problem. And so the problem that I see with this type of techniques is that then it's more or less up to how powerful is your encoder and decoder to be able to compress the information down to lower dimension and decompress it back. And it doesn't tell you much about the intrinsic, independent degrees of freedom that you would understand as part of a physical model. So I haven't seen a very compelling example of being able to discover this kind of, intrinsic properties that you describe from a neural network.
I just want to mention, we're also discounting the impact of choosing an architecture on the description of latent space as well. So we did some work on this, very similar to what you described inside of trying to enforce disentanglement in latent space, and seeing if there was a physical mechanism behind the dimensions. And we found that it was very sensitive to the architecture that you used. And the most classical example is if you just think about a circle data distribution, right? You can explain that with one number, just the angle of the circle. But it's a lot easier for a neural network to learn two numbers, the x and y position of where you are on the circle. And so any neural network that we use, yes, optimally can be compressed to a certain number of latent spaces, but also is highly dependent on the architecture. And I apologize for the self-promotion, but I will talk about that project as the last talk on Friday. So.
Well played, Matt.
We have two comments here in New York. So, Peter.
I think it's pretty dangerous to try to find dimensionality in latent space. They're so permissive, they'll handle 2 parameters, 5, 10, whatever, and they'll be good even in low dimensions. I think what is important is that we may not have enough data to really fully train out something that is not actually a well-chosen architecture. So I think choosing the architecture, so hearkening on what we just heard, choosing the architecture is really important to come to a latent space that is in fact highly informative and, if you will, kind of highly compressive. And so I think there's more in the getting into the latent space and what data we use, what architecture, and whether those two match and work together with each other in order to establish something like a useful model. But low dimensionality is the outcome of that. Trainability is the outcome of having this, but it's not some kind of inherent property that would emerge.
Yeah, and my comment is actually related to the white box comment. I actually agree to an extent that like having at least partially white box models is actually a good thing for interpreting the latent space. And the simplest example would be having a CNN working on images, and you are not only trying to interpret the latent space and how that distribution looks like, but combine that with methods that like saliency maps that would tell you a little bit more about the filters themselves so that you understand what other layers are actually doing. And if the latent space is built on the properties that maybe you find useful or logical or that align with the things that you think is important about these objects, or more importantly, if the models consistently find something weird and use something weird, is this something that we haven't thought about and might lead to a new discovery, or is a problem in our data set that we were not aware of? And the simplest example of that would be medical imaging and the famous example of different hospitals having different names in the bottom of the image and classifiers working perfectly just because they were locating the name of the hospital the image is coming from. So if we were looking at the latent space of that model, maybe we would not notice that this is the problem. So like having a little bit of white box properties of the model is useful.
Well, I mean, I think the problem with the saliency methods and these kind of more visualization tools is the fact that you never really get a quantitative answer from it, right? So you get some qualitative understanding of the scales that, for example, matter in your input image or whatever it is. But I think with the latent space, you actually have a way of imposing, you know, constraints that are mathematical and then actually analyzing that in a quantitative way, for example, with mutual information or anything really. Whereas with the saliency maps, you're really just left with a map. And then it's like, well, okay, I can see that the information is here, but unless you have, you know, some specific edges or, you know, some specific features that you can directly pull out from visually, then I think it's really hard to make any actual, you know, scientific discovery from that.
If I might add, my idea was just to combine the methods, not really, I mean, of course, both of the things are useful. And I think the only worry I am absolutely for constraining the latent space. I think what I worry about in this case is, what if we're constraining on the beliefs that are wrong that we already have? So, and also how do we allow the model to constrain the things that we want, but also be free enough to encode the other things that are unknown to us? that we might miss if we constrain everything about it. So that's kind of, I don't think that we're there yet, but I feel like that's something that we really strongly need to think about.
So we have a question on Slack to end this block. Let me see.
To who, sorry?
Yes, please.
Okay, so no, there is, because there is 2 questions, and okay, so the first one is, what about model trained on one data set applied to another data set? How much belief should we put on truth found in this way?
Okay, how much truth should we put on what?
On truth found in this way, when we apply one model trained on one data set to another data set.
It's probably a question for
anyone
Alex.
entitled?
I can maybe, I guess, talk about it because I think about it every day. I think this relates to the comments that you can build different types of latent spaces on the same data set based on the architecture that you choose. So in this case, we should know that we are aiming to apply our model on different data sets or all data sets, and that we actually care about building a model that is robust across all of them and not very focused on data set specific properties. So if you're not thinking in advance about this problem, building a latent space can include a lot of data set specific properties and in that case, this truth is not, I wouldn't say it doesn't fully apply to the new data set, but it will be flawed because some of the parameters of the latent space actually encode data properties that you might not care about. Like if you are trying to figure out the physics of stars, you don't care about the PSF or the telescope or the noise levels. So you have to know and believe that you're building a latent space that also doesn't care about these nuisance parameters. So yeah, I guess it all depends on how you build the latent space.
Okay, there was a second question, correct? Yeah, please. We are getting a bit.
And there's a comment in New York as well. So, Torsten, you go. You order.
Yeah. No, just the second question, and then we go for the next talk. You have an option to ask your question then in the next block.
Hopefully, the comment in New York as well.
Yeah.
Okay. So it's about the distinction between latent space vis-à-vis traditional phenomenological model building. Aren't both instances of model construction with somewhat ad hoc model parameters?
I didn't get it fully, sorry.
So the question is a distinction between latent spaces and traditional phenomenological model building.
Okay, so the difference between latent spaces and traditional phenomenological models, I would answer a traditional phenomenological model is a latent space. A handcrafted latent space. And they can be very powerful. So let's do a little bit self-advertisement. That's what my group does in information field theory. We build generative models, neural networks where you can understand every layer by hand, encoding the physics. Okay, let's get the discussion into a different direction. And we have François.
Okay.
So here is, can we, yeah, I just press on this, and the next slide is yours. Can you, come here.
Yeah, I can see it. All right, so I tried really hard not to spoil my point of view, so I'm happy to be able to tell you about the way that I think about this problem. So is there truth in latent space? Yes, for some definition of truth. And the statement, the kind of controversial statement I wanted to make is that this truth is not necessarily what we care about for my particular interpretation of that truth, what it means. So the way that I understand this is saying, as I think Torsten was saying, is that there is information about the true latent generative process, the true physical process, and the true physical parameters that describe your problem somewhere in any representation of your data. And so in that sense, if I build a model that can generate examples of my data and I fit that model on the particular data, I have some matching of information between the true underlying process and my empirical model. The problem, though, is that this information is typically, when you use neural network, encoded in a very arbitrary way. And this is kind of the example of things that happen by accident. Let's say, because we don't really know how to explain it in practice, why a particular autoencoder, for instance, is going to be able to encode the information in this latent space in a certain way. This is kind of something that happens by accident if you see some interesting patterns in that. It's not something that the model has been necessarily trained or incentivized for doing. So that information that you may be able to access in the latent space of something like a variational autoencoder, it has information about the data, so about the underlying physical model. And so it can be useful as a summary, but the kind of controversial point that I want to make is that in general, this is not information that you know how to interpret. So then what is the real question? The real question for me is that if you ask the question, what, is there truth in latent space? The real question you want to ask as a physicist is, can the machine actually exhibit emergent physical wisdom? And by that I mean, find a way to represent the information that is either interpretable or that discovers automatically, let's say, physical factors or variations in your data. This is the real thing we're interested in terms of discovery, is to see structure emerge from the data, and the structure should align with the underlying physical processes. So that's difficult. That's not something that we see most of the time in machine learning models. And so far, I would say that I haven't seen very overwhelming examples of being able to discover such structure automatically. And so, for instance, one question I asked Peter earlier today is in his variational autoencoder, if you remember, he had an additional loss in the latent space. And he said that without this loss, the structure of that latent space wasn't really physical or well-behaved, let's say. And so you have points that have very physical properties that are far apart in this space by accident because of the VAE, is not really incentivized to discover very intrinsic and meaningful representation of your data. But I'm still hopeful for the future because you see a lot of interesting trends in modern machine learning and in the space of the things that they call large foundation models. And in particular, everything that has to do with contrastive learning seems to work really well to discover a very interesting and deep meaning about your data, for instance, on natural images. So here I have a small illustration that we don't really have time to talk about, but the main point is that those contrastive learning methods, in some cases, and in particular in this paper that I find very interesting, you can think of them as inverting some sort of data generative process. So they're able to discover a latent space, so the inverse mapping of some unknown forward mapping, which doesn't necessarily mean physical mapping in that case. But what turns out is that the space that they discover has additional nice properties compared to something like a VAE. So for instance, they tend to embed in that latent space objects that are physically similar, close to each other by construction. And that's not something that you have in the VE. And then you can see a lot of downstream application of these things in practice where, for instance, a model that has been trained with this sort of contrastive learning laws, then with a very simple additional mapping, you can extract physical properties, like, for instance, depth map on natural images, or just segmenting the information in the map. So I want to believe that these kind of methods, although I'm not super happy about them because most of the time so far we don't really know how to explain them properly, but they go in a more practical way towards this alignment of representation with physical information, and then you can decode that information with usually very small models. So they make me very optimistic about the future, and these days I'm mostly working just on that. That's the end of my statement. Happy to take any questions.
Okay.
There was a question in New York, but yeah.
Oh.
We have Mike.
Yeah. Let's do New York first because it's so hard for them to get through to us. So please.
Ashley, please.
You hear me? First, excellent statement, François. Totally agree. And I think it goes back to this point that I do not quite believe yet that anyone's really extracting any meaningful physics from a latent space. That is not what's happening. Instead, we're imposing physics onto a latent space to help it some level of interpretability. And I think latent spaces are only as useful as much as they can perform well on downstream tasks. That is, to me, the importance of these. And I guess I have a question for François that goes back to something you said much earlier. One of your first comments was, and I might be not quite remembering, but that you were saying, oh, well, you know, in this interpretability, I can do these downstream tasks like some regression problem where I can just marginalize over morphology. So I guess the question I have for you is, how are you so convinced that you can interpret your latent space with such confidence that you can, in fact, marginalize over something like morphology?
Yeah, exactly. So the question is, what do you want to discover and what do you want to impose? So if you're thinking as a physicist, you're only satisfied when you come up with a model that has a small number of parameters and that you think makes sense and that you know how to describe, and that each component you can give a meaning to, that can generate your data. So from that point of view, if I'm interested in, for instance, measuring wig lensing on the sky and doing cosmology, I can write down the entire model that links cosmology to the images, and I have a piece in that description of this entire model that is there for modeling the galaxy morphology. And that piece, I know, I can point to it, I can describe it, and I don't really know, I don't even care what goes on in that piece. So that's, in this way of thinking about how you build the entire model, you can have a little pieces here and there that you don't know exactly how to model, but you can represent with a black box machine learning model. And so they segment, let's say, your latent space into something that is purely physical and some things that are empirical that you don't really care about.
I'm so sorry, one follow-up then. So then that is only guaranteed to be true if that is a strong regularization, like you've built that into the architecture. So then should we be messing with our loss functions to have regularization, or is that, because that's not always guaranteed to be true?
So I think it comes down to how you structure the model that you use to apply the data. And so in general, in most of my research, whenever I know that there is a physical way to incorporate an effect, I will use it instead of hoping that the network will learn it. And so another example we saw today is, for instance, Peter using like his physical understanding about the redshift in his autoencoder. This is not something you need the network to learn. So that's kind of how you decouple the machine learning part for the things that you're okay with leaving as a black box, and the explicit physical part for everything else that are just extremely important for your understanding of the physics.
Okay.
Maybe I just wanted to say that, why do you say that VAEs do have explicitly promote disentanglement in latent space? I mean, the example that you brought up of Peter's work, the reason why the latent space looked crazy without that loss is because I think he didn't have disentanglement in his latent space. If he did, then I agree that it's not exactly the same as contrastive learning, but you still get similar points in data being similar in latent space. Oh, sorry. The problem with contrastive learning is that you have a dimensionality of your latent space that is like of thousands of dimensions, right?
But
so
is
then,
that a problem? That's an interesting question.
Yeah.
So, yeah. I've been thinking about this, and I don't think it's a problem. It's actually a feature. It's not a bug. Because you can represent the information in so many higher dimensions, it's much easier to have objects, to force them to be close together along many different factors of variations. So if you need to compress everything down to a 2D space, for instance, then if you want two objects to be close together in terms of let's say, galaxy mass, redshift, color, whatever, it's very difficult to find a way to arrange the data in that space. But if you're in a high-dimensional space, it's very easy to align things across many dimensions. You have a lot more freedom. So it's easier for the model to extract, let's say, a notion of similarity between objects, explicitly in that case with contrastive learning. And that gives rise to very useful downstream applications, such as looking for similar objects just by comparing the alignment of their embedding. And it's the equivalent of what, let's say, Peter was doing with this explicit constraint. It's the same thing that happens in. So I don't believe in the low dimensionality compression of VAEs anymore, and I want to give the freedom to the model to embed this in some linear space. So the important second point, thank you for, I forgot to mention it, is that when you go into this high dimensional space, then the information is a lot more accessible. It's easier to decode because it's not compressed as much. And so what you find with this kind of model is that you can extract very easily by just a linear mapping a lot of downstream information directly from that embedding space in a way that it's not necessarily as easy to do with a variation autoencoder. If that, yeah.
Okay, last question for this block over here.
François, I had trouble understanding why you said that we have not gained any wisdom from an analysis of latent space. And I'll give you an example. If I give data to one of these machines of a pendulum swinging at different times, wouldn't it find that there might be a force equals mass times acceleration and the constant gravity law, to make it simple?
So sure, it will. I mean, it will be a fitting function.
And it would be a very simple one, which would be very beautiful and might be very convincing for us compared to other solutions it might find, which are equally probable but highly complex.
So in practice, people have done that. Manoj Kramer, for instance, has done a lot of nice work of distilling neural networks into simpler formula. But the thing that you have to do usually in these cases is to impose very strong constraints on what you think is going to be a good way to parameterize the solution. So for instance, if you want to discover gravity, you will then allow particles to interact with each other with simple relations, and you can even constrain that there are just a few degrees of freedom, or you try to specify the messages between particles. So you already impose a lot of your prior expectations about what you want to discover, and that's usually what I find in practice, is that you've done so much work to force the network to do what you want it to do, that you have not really learned directly things from it. And this is, the goal, or the hope of what we would like to see with this kind of model, is that you just throw data at it, and then there is structure that emerges, and you can interpret that structure without you having to put a lot of insight. And that I haven't seen happen too much in real life.
Maybe there's a question in New York or on Slack.
Hi from New York. I just wanted to put together, if you combine Peter's comment that many models are designed to be trainable and optimizable as opposed to efficient, and you put that with François' comment that high dimensional latent spaces are useful, and you combine it with Ashley's comment that maybe the only thing we need is an effective prediction model. Like, that's really useful itself. If you put them together, there's a tension really, because if you want an interpretable, useful latent space to see how much you can compress stuff, etc., it makes it actually harder sometimes to make an effective prediction model. So the question is then, are there cases where we're willing to just say, there might be truth in latent space? It's not the truth I'm going for. I'm building a useful black box.
Sure, yeah. That was part of my point. Yep. I usually don't care about latent space.
Good. Let's see how the last of the four panelists sees this. So let's switch to the presentation in New York. Aleksandra.
Okay. I tried not to mention too much of the things that I was planning to talk about in my comments, but I think I failed at that. So when I was thinking about the truth in latent space, I'm one of the people that believes in ML. So like I would say yes, definitely. But is it the truth that we need? It depends highly on the task that we want to do with a machine learning model. And so I think before building a model, we have to ask ourselves very carefully, what do we want to do with it? And then try to pick a method to train the model accordingly, such that we build the latent space that is useful for that particular task. Of course, there is a whole area of like fundamental AI models, foundational models that are trying to like get to the actual core, to the truth. But in many cases, in many applications, we're not really trying to do that. The question that I've been mostly asking myself is a bit more forward-looking, because I feel like currently there is a limit to all of the models that we're building, and we're not yet able to utilize AI fully for actual like new discoveries or for pointing out new physics or weird things, because we're usually constraining it only based on the things that we know. So the thing that I want to ask is, can we build a method that is good at being constrained by the physics that we know, but also has enough freedom to encode anything else that we might not understand or know in some additional latent space features, but in such a way that we can actually understand it. So I think these are actually two different tasks. One is giving it enough freedom to encode everything that is actually there in our data. And the second completely different task is how do we translate that into something that our brains actually understand? Let me see. And so I have an example here, which is based again on the contrastive learning that I also started really liking lately, which is a model that where we build a model to classify and build a latent space that can classify things across different data sets. And in here you have the violet ellipse and the blue one represent two data sets and two classes that actually overlap in these data sets. So the empty and filled triangles and the empty and filled circles. But the idea is what happens if, can we build a latent space that actually can understand that there might be a new class in one of the data sets, which in this case is the yellow axis. So can we build a model that maybe has never seen a labeled yellow X? In this case, these are actually strongly gravitationally lensed galaxies. So can we understand, can we build a model that learns, for example, all of the features of regular galaxies, but understands when it sees a new gravitationally lensed galaxy in the new data set that it wasn't trained on, that this is something different that should be pushed to the side and not really align with all of the regular galaxies. And indeed we can. So I think to an extent I can say, yes, this latent space has the truth that I need, which means in this particular case, my truth is, can I discover, for example, strong gravitationally lensed galaxies in the new data, even though I have just a few examples, for example, or none in my previous observations. So as I already hinted previously, the other thing that we have to think about is, can we understand the truth? So I do believe that we can build latent space that contains truth that is correct for a specific data set, but can we understand it? So I'm also prone to not trying to force the latent space to be very small, because I feel like we're losing the potential of encoding extra stuff. But we have to find ways, and I again think that there are many methods there, but we're not fully there yet, that can help us translate these high dimensional latent spaces into something that we understand. So of course, I mean, there are methods that shrink that into smaller dimensional spaces like isomaps, UMAP, and so on. But I was actually really interested in Peter's comment in his talk where he mentioned normalizing flows, because then you can actually use a normalizing flow that can make a very much more complex but invertible function to actually go from a very complex latent space that means nothing to our brains to something that can be more interpretable. And you can also go back and forth. So I think this is a very promising new avenue of thinking about how to interpret latent spaces. And again, want to emphasize that I feel like it's important to connect the latent space to the other layers of the network, so make it a little bit more white boxy so that it can help us in our interpretation. And I feel like this is particularly important when we build models that might have trouble with outliers or some anomalies or perturbations and things that might be problematic with our data that we might not be aware of. So we very well know that a pixel can, wrong pixel in the wrong spot in an image can trigger the model to do the task incorrectly. So how can we build a model that is robust to all of these things, even in cases when we don't know what kind of problem is contained in the data? And this is going to be often the case. So I think, yes, I'm going to end there. Thank you.
Thank you. Maybe you go a slide back, since we can still discuss for a few minutes your topic. Okay, New York, Slack, Paris, France, Australia.
We have one comment here.
Can you hear me?
Yes,
okay.
Please go ahead.
So all of these comments, like the way we are defining truth and the way we are defining a latent space, have been very illuminating. I guess my question is, what happens when the truth is bigger than our brains, in the sense that if there is a truth that's inherently more than three-dimensional, then visualizations, like you mentioned, might help, but like essentially, like if our latent spaces are learning a truth, how do we learn that from looking at the latent space?
It's a very tough question. So I think, as with any other methods before AI, we have to kind of poke it and try to see if there is something that we can conclude from it. But I honestly don't think that we will ever be completely certain that we have been able to fully interpret it. So yeah, I don't know, it's tough.
Okay, maybe a question directly from the latent space. Yeah, Ben.
I mean, this is the conceit of science, that we believe that ultimately we can find low-dimensional representations, maybe many of them stacked on top of one another, that allow us to interpret and predict the world. If we give up on that, then that's very problematic. And at least so far, that approach has been spectacularly successful. So the odds are that maybe it'll carry us a little bit further. Now the question is, maybe we can interpret what we're trying to do here, or call it by what it appears to be. We're trying to leapfrog this process. This process tends to be a very slow process that takes hundreds of years to build these interpretable small number of degree of freedom models. And what we're trying to do is accelerate that massively by using these new techniques that seem to be so good at predicting the world, even though it's not completely open box. And so the utility of that, there's great utility if the prediction is the key. But then the interpretability, which is the question we're asking here, in terms of the latent space, I guess, if you take utility and you put a minus sign in front of it, then it becomes loss. And the loss is what we use to train these networks. So until we figure out how to put into the loss that, please, we would like to have an interpretable or physically meaningful representation, until that point, I guess we're not going to conclude on this matter. And then maybe as a last point, I just want to recall the quotation by Arthur Eddington, who said, I'll paraphrase, that you should not believe any observational data until it is confirmed by theory.
Karim?
Yeah, actually, I have no citation to offer, but I wanted to push perhaps a bit on the line on, a bit on the line of what Ben said. I mean, we discussed a lot about normalizing flows, variational autoencoders, where we kind of see what can be this mysterious latent space, where we can find something which is lower dimension. There is something that we've discussed a lot yesterday, which was symbolic regression, where you also get to some kind of latent space with less dimension, less parameters. So is there truth in this, what we get out of symbolic regression as well? Do we expect that we'll get truth somehow? 2 years ago, we had a presentation which was like trying to recover a Newtonian physics from data in a symbolic regression way. We have even more of those talks this year. What can we make out of that, and where are we going this way? Is it a way to get truth?
No. This is what I was saying earlier, is that so far, the way that we've been doing this symbolic regression thing and trying to make it interpretable, that we have very empirical way to force the relation that it's describing to be sensible or simple to some extent. But they are not deep ways of describing what we mean by simple relation or meaningful relations. But because now we are in the realm of large language models, I wouldn't be surprised if in the next few years or so, you have a combination of the language model understanding of what every physical piece in your equation means, combined with the effectiveness of that relationship to represent the data, to be combined in a way that you have sensible way of constraining the type of equation that can arrive in a given context. And then at that point, I would feel optimistic that you would be able to obtain equations that would make some physical sense because they build on your prior knowledge about the meaning of a particular term in an equation.
Yeah, I think I agree. I mean, I think it's possible that, yeah, we'll be able to actually impose some better, constraints on the terms and understanding the terms, but right now it feels like you get some really complicated equations which don't really add interpretability to it. I just wanted to add that, going back to the VAE, there have been papers that have shown that just by imposing disentanglements, that isn't like a physical constraint, right? It's just imposing completeness, continuity, and these kinds of properties to the latent space. They have recovered things like, the physical parameters of a double pendulum or things like that, automatically without imposing anything physical on it. So I think there are, ways in which you can constrain properties of the latent space that are simply like smoothness and completeness and potentially recover physics from it.
Yeah. There's a comment on that in New York. So,
thanks. Yeah, so I heard a few different remarks about the idea that we're not really discovering, with a high signal to noise, like new physics or evidence for new physics in the latent space of the models that we're creating. And I wanted to ask the panel whether we think that's mostly due to the way that we're setting up our experiments, the way that we're pre-processing our data that's going into these models. Are we doing that in a confirmation biased kind of way that is leading us to find what we're expecting to see? Or is it the case that any novelties that are there to be discovered, the signal of that is just way quieter than the physics that we already understand?
Probably some combination of all of the above. I mean, but maybe the best answer that we've heard today is something that Ben said earlier, is that this is not the target. You're not training those models to explicitly discover space that would be interpretable. And as a result, we're trying to infer some meaning of the space that it discovers, but any space that is discovered with these deep learning models is more or less by accident. And then you can try to constrain it to go in some particular direction by imposing some disentanglement. But it's, in all cases, it's not, you're not optimizing something to generate an expression that is interpretable. And I think that's the core issue. It's not the, we're using a tool not for the thing that we're optimizing it.
Okay, we have a Slack question.
So for contrastive approaches, do you really have the learning task that will work well for astrodata, which is much simpler than natural languages or text? Basically, what is a good contrastive loss for data with low complexity and information density?
So that's a good question. So maybe I guess the core question here is that when you want to do contrastive learning, you need ways of augmenting your data that does not disrupt the physical meaning of whatever object you're looking at, but that seems to be like a different view, independent view of the same object, and that preserves the same physical information. So the problem is, if we have very simple data, then there is not a lot of ways that you can do those perturbations without changing the physical meaning that is behind them. So one thing that I'm pretty excited about is to try to see if you can use different types of observations that essentially are looking at the same underlying physical object, but through different means. So for instance, you can have an optical spectrum, or you can have an image of a galaxy. They are two independent views of the same underlying object, and you don't need to do any data augmentation in either cases, because those two views are actually related to the same underlying physical parameters that describe that object. So I believe that one interesting way that we can solve that problem is by combining different type of observation from different modalities. And then you don't need to do any data augmentation.
Okay, thank you. Get the presentation back to Paris.
There is another comment in New York if you want. And yeah.
Yeah, how are we doing with time?
We're fine.
Okay.
We need to wrap up, but we're fine.
Some of us are hungry, by the way, but yeah. Please.
Okay.
So one thing I find, and it's a bit philosophical, one thing I find problematic is the way we've done physics for a long time is basically looking for simplicity. Like we do Occam's razor, and that's how we define whether one theory is better than another. Just look for the parameter, look for the model with fewer parameters. But now we're massively over-parameterizing problems with neural networks, and we have a latent space that is, massively large and maybe much larger than we ever need it to be. it's strange that we then say that is more truthful, or that has some truth. And so a question I might have is, suppose you did have a generalizable neural network that could perfectly predict all of physics, standard model, cosmology, and everything. Would we then say that that is a truthful model because it does the job well and it follows all of the evidence and it predicts everything reasonably well? Or would we say that it's wrong? I mean, we have a cosmological model where we don't really understand lambda or CDM, but we use it. Can we do the same thing with a neural network where we had something that has a very large dimensional space, a large parameter space, and we can make good predictions with it, but we don't understand those latent parameters well enough?
So this is a bit like Feynman's proposal for a unified theory, where he said, just combine all equations we know in physics into one equations, and then we have everything. So is this your point?
I mean, kind of, but it's more than that, because I like personally, I feel that a little bit problematic, right? You can't say that, I've got this neural network with 1 million parameters, obviously over parameterizing a problem, but it makes all the predictions well enough, right? It's all perfect. I wouldn't find that a reasonable, or I wouldn't be happy with humans as finding this is the solution to the universe and the fundamental, solution, if that's what we're going with, right? I'd rather understand what's going on in the problem. So is that true?
Yeah. I like to answer, to comment on that. I think we need to understand what prior knowledge we impose when we use a different specific architecture or different ways. I think the connection between the implicit priors we get by using different architectures and what kind of prior we actually would like to have is completely unclear in most cases. Not in all, in most cases. That would be my take on that.
But I will also add that you're very right that you're putting your finger on the real problem is that we don't care about just having a black box function. We want to have a meaningful description of that meaningful model that can describe the data. So you don't want to have just one thing that you cannot interpret. That's not a good use case for neural networks, I would say, in that case.
Okay. So let's get back to the last presentation. That's by myself. Can we get the Paris presentation on the screen? Yes, thank you. So when I was planning to moderate this, I was fearing that every panelist could say the same. That's the worst situation. So I thought, what can I put in order to put a little bit more entropy into the debate? And so here you see my attempt. So that's my claim. Attention is a resource. What do I mean with that? So let's look at these two persons here on the left side in this bar situation. Let's give them a name. Let's say this is Alice, and that's Bob. And Alice has an internal state. She knows something about the world. And that implies the probability distribution about all the different states the world can have. And Alice is nice. She wants to talk to Bob and let him know something about her knowledge on the world. And so Bob will get also some internal state and can construct a probability. Alice and Bob don't need to be people, right? Alice could be the input layer of an autoencoder and Bob is a latent space. Or Alice is a latent space and Bob is the output, right? So here we're talking about communication and how to design communication. That's actually what's happening in all these neural networks. That's happening in our brains between the different layers. It's happening here between two continents. It turns out that a very fundamental principle to be used in order to design communication is entropy, or more specifically, the relative entropy between the probabilities of Alice knowledge and the induced Bob knowledge, and that measures the information loss in nits or nets. The problem with this thing is, despite that one can derive it from a number of axioms and argumentations, the problem is that it measures everything with the same weight. Something which is relevant gets the same number of bits than something which is completely irrelevant. So maybe one can introduce some relevance into this. Let's try this for a second. So let's just weight probabilities and replaces this equation, and you get this equation, okay? You see parts are irrelevant, turn out, and then you still have a weight which makes a difference. So if you use this in order to design communication, it is terrible. Don't use it. It is not proper. So Alice will not, even if she can, inform Bob properly if the weights are structured. So why is that? Let's look at the formula again. What you put in are probabilities. Probabilities are normalized. The weighted probability is not normalized. So let's normalize it. And let's give it a name. And I would call it attention. So probability times some importance, just normalized, has a property of a probability. You can plug it into this formula and it works perfectly. It is proper, meaning that if Alice uses this, she will inform Bob precisely if she is able to, and otherwise she will put the attention where it belongs, where it's most important. Okay, so attention is a resource. If you want to read more about it, there's a paper, but the statement is it allows to weight latent space or other spaces. So maybe it can put the weight on what is important or where there's a truth, but it is limited. If you increase the attention for something, you have to decrease it for something else. So I hope I got your attention, and if you want to shoot for 5 minutes question on me, please go ahead. Yeah.
So, is New York very angry, or is there questions there before we wrap up?
He's pushing. Any question here?
Did I get anybody's attention?
Maybe I can
guess so.
So how do you, in this case, how would you decide what to weigh more? Would the non-known physics be weighted more, or do you prefer to find new things and weigh more the known physics?
Yeah, so in this case, it's just a language you can use. What you put in the weight is still a decision. In that publication, you'll find a communication scenario where these weights derive from a utility in a specific case. But that is maybe connecting to Ben's comment. We should look at utilities, and utility induces this structure in the spaces in which we represent information. So either you can derive it from a utility, or you put it in by hand, or maybe someone else has a clever idea how to use this. But so this formula, this relative attention entropy, can be as rigorously derived as relative entropy in a communication setting.
It's probably a good conclusion, I say.
Okay.
So thanks a lot. Thanks for the debate.
Yeah. Thank you, everybody, and have a nice lunch or dinner.
Thank you, guys. So for us, let's
and
have
we
the lunch.
tomorrow for reviews, of course, at 10.
And we come back at 3 p.m. for the talk
Good rest of the day to New York, good lunch, and good reviews on your side. See you tomorrow.